Today I'm going to explain integral test and a p-series. But before we go on an integral test and a p-series, let's review about the geometric series. So here is the past AP question, and let's take a look at this as a warm-up. So this is infinite geometric series. You can see that exponential function look alike. So this is a geometric series. And the common ratio R is a 1/3, which is a base, which is less than 1. So we know that this series converge. They did not say anything about evaluate or anything. They just put equal to sign. So which means find the sum. So sum of an infinite geometric series is a first term over 1 minus R. So in this case, R is a 1/3. So 1 minus 1/3. And the first term, if you begin with n, is 1 over 3 to the n. And this becomes 1 over 3 to the n. 1 minus 1/3 is a 2/3. And clearly you can see that 2/3, if you flip it, it becomes 3 over 2. So this is the answer. Let's take a look at another one here. Okay, so let's check this out. This says 2003 multiple choice question here. Again, what is the value of this? So in other words, what this is equal to. This is a look-alike geometric series. It would help you so much if you rewrite as a exponential function or expand. So I'm going to show you the properties of exponents. 2 to the n, 2 to the 1 over 3 to the n, which is 2 times 2 over 3 to the n. Clearly, common ratio is a 2/3. Sum is 1 minus 2/3. All we need is a first term. So very careful, first term starts with 1. So 2 to the 1 plus 1 is a 4. Divided by 3 to the 1 is a 3. So how do you simplify this fraction? 1 minus 1/3, 2/3 is a 1/3. And 4/3 over 1/3, answer is a 4. Not bad, right? Okay, well, I have one more problem in case if you are interested in. Let's take a look at this 1993 BC3. This is very interesting question. So it's asking for interval of convergence. Interval of convergence, what that means is for what value of x this series will converge. Okay, so what values of x this series will converge? In other words, what value of x this will become geometric series? So if I rewrite as a geometric series, x minus 1 to the n, 3 to the n is x minus 1 over 3 to the n. Now think about the common ratio. R is x minus 1 over 3. It says convergence, so assumption is that this series is converging. For a geometric series, we know that the common ratio has to be less than 1, then only this series converge. So we are going to substitute x minus 1 over 3 less than 1. Let's solve this inequality. X minus 1, if I multiply both sides by 3, is less than 3. Now in Algebra 1, you learned the absolute value function. So in other words, you can say the distance is the center is a 1 and less than 3. That means this is the radius. If I go 3 units this side, so it will be 4. And if I go 3 units in the back, it will be negative 2. So clearly less than means all these values has to be between less than 2 and greater than 4. So if once you come across here, you can clearly eliminate these choices. That maximum is on this side, add 1, you 4, and you go on the other side is now You should know also that the geometric series, the ratio has to be less than 1, not equal to. So clear choice is this is the answer because there is an equal to sign and we cannot use that. Okay, so now let's come to the integral test. There are two tests. One is called integral test and one is called P-series. Make sure you know them both very well. In this series, in this section, we will look at this series with positive terms. So know that integral test and P-series can be applied to series which has only positive terms. What that means is you cannot have this part. You cannot have alternator, not allowed. In other words, no negative sign. Coefficient is fine, but the variable cannot be negative. So let's take a look at the integral test. Okay, so the integral test says if f is positive, continuous and decreasing for all the values x greater than 1, then we are going to look at the series as a function. Any series a of a sub n, we are going to make it look like it is a function. So series we rewrite as a function and then we evaluate this improper integral. We have to evaluate this improper integral, and if this integral converge, we can say series converge. If integral diverge, we can say series diverge. So in other words, we are going to rewrite this function series as a function and we are going to check if integral converge or diverge. So this is another reason we learn how to evaluate improper integrals. Clearly you can say 1, infinity, infinity, summation to integral a sub n is f of x, and then we just have to check. Now, interesting thing is, if integral converge, we cannot say that is the value of the series. We can just say it converge, that's all. Function need only be decreasing for some values of k. So the most important part is you have to check whether series positive, continuous or decreasing. Then only you can apply this test. Then only you can apply this test. So to check if the function is decreasing, obviously we have learned that to find f prime of x, and if f prime of x is less than 0, then satisfies conditions for the integral test. Now the good news is many times you just have to mention that, you just have to check, you don't have to prove that the function is decreasing, continuous or positive. And always remember, you can write whichever order, D, C, P or PCD. Know this word positive, continuous, decreasing, then only integral test. So let's take a look at here. Okay, so this is the first example I'm checking. So in the past we have learned nth term test. Can we apply nth term test here? Let's take a look at that. Nth term test says last term is 0, last term is not 0, then series diverge. So clearly this is a bottom heavy. So nth term test fail. This doesn't look like a geometric series, so that's not the question here. Now checking positive, continuous, decreasing. So this is a bottom heavy, that's why decreasing. Denominator never becomes 0, that's why continuous. And you can see that if you expand, all the terms are going to be positive. So you just have to write down that all the terms are positive, continuous, decreasing. That means you can apply the integral test. Okay, so let's see, how do we apply the integral test? How do we write it? Check positive, continuous, decreasing. Okay, so the first thing is you have to rewrite this as f of x. X over x squared plus 1. Then limit, no, not the limit, we don't have to, I'm sorry, we don't have to write the limit yet. We just have to set up the integral first. just have to set up the integral first. I apologize. This is little slow here. Okay. Got it. Okay, so 1 to infinity x over x squared plus 1 dx. This is improper integral. We don't have to prove continuous positive decreasing, you just have to check. Okay, to evaluate, we have to change it to the proper integral. If you recall, b approaches infinity, 1 to b, x over x squared plus 1. Good news is almost most of the time evaluating integral is always going to be very easy part here. So clearly we can see that you can apply the u sub. Derivative of x squared is a 2x and I don't have a 2. So which I can change it here to 1, 2 and 2. One and 2. No, 2x and 2x. There we go. So antiderivative will be 1/2 ln x squared plus 1 and the bound is 1 and b. So if I bring down the limit statement, limit b approaches infinity, 1/2 ln b squared plus 1 minus 1/2 ln 2. Okay, so let's look at this part. What's happening here? B approaches infinity, ln b square is infinity. We have this answer, but this is infinity, and we can say integral diverge. Therefore, series diverge by integral test. You have to give the name of the name. You have to say that by what test. So don't get discouraged by the integral test. There are many other tests also which we can apply here, but in the exam, if they say that use integral test, you have to use integral test. You have to use integral test. So for now, let's just apply and see how we can use it. So in this case here, let's take a look at one more here. Continuous, we can see that denominator never becomes 0. 1 to infinity is continuous. So f of x is 1 over x squared plus 1 dcp, decreasing, bottom heavy, continuous because function has a no asymptote, vertical asymptote. It's 1 to infinity and it's always positive. Denominator is always positive. So if I apply the integral test, I'm straight away, no, I should write the setup. I must show the setup. I apologize. I jumped straight to the limit statement. And Promethean software is also not very helpful here. Okay, so 1 to infinity, 1 over x squared plus 1. Limit b approaches infinity, 1 to b, 1 over x squared plus 1 dx. So do you recall this integral? Do you memories coming back? How do we apply this? This is limit b approaches infinity, tangent inverse. And tangent inverse b minus tangent inverse 1. Limit b approaches infinity. If you recall, then tangent inverse graph looks like this, and b approaches infinity. This is pi over 2, and tangent inverse 1 is pi over 4. So pi over 2 minus pi over 4 is equal to pi over 4. Therefore, series converges by integral test. So another reason tangent inverse function is always important, and you must know the end behavior of tangent function, tangent inverse. So the question is is this equal to pi over 4? Question mark, which is no, this is not equal to pi over 4. The sum is not equal to pi over 4. We can only say that integral converge. That's why this series converge. Okay, so one more here. This is the most popular one, 1 over n. So clearly f of x is equal to 1 over x. We know that 1 over x is continuous decreasing pole, positive. I always say that use the DC police department. DC police, decreasing, continuous, positive. In the assessment, of course, you have to write it up that this is decreasing, this is continuous, this is positive. So let's set up the integral 1 to infinity 1 over x dx, which is limit statement. Pay attention to this problem. This is very important one. Limit b approaches infinity 1 to b 1 over x dx, and clearly this is ln x 1 and b. Limit b approaches infinity ln b minus ln 1. ln 1 is a 0. And obviously log function is the slope. It slowly rises to the infinity, and this is infinity. And series diverge because integral test diverge. Integral diverge, so series diverges by integral test. Okay, so interesting. This is the extension or introduction of a P series. This is also known as P series. If you recall that improper integral, we did this in Unit 6b. Recall that Unit 6b. This is a P series. P is equal to 1 is always diverge. Unit 6b, improper integral. If you find out that packet, we talked about if P is 1, diverge. And let's talk about the P series on the next page. But before we go there, we have to understand this inequality. So let's talk about this. There are multiple choice questions regarding this inequality. So what that says is, think about continuous decreasing positive, this kind of functions. And if you use a Riemann sum, this is a kind of a Riemann sum, and this is the actual integral. So difference between series and Riemann sum. This is an integer. It's very interesting to understand. So if we make it continuous, then we can see that the red color is the area which is lower than the green color. So understand this part is less than. The integral value is always going to be the less than the series sum, the sum of the series. Integral value, because this is the red color, is the actual graph a of x, and this is the summation of that. It's always less than. Clearly you can see from this picture. So many times they have asked this as a multiple choice question. Always sketch the picture and see that this is the right Riemann sum, left Riemann sum is always going to be the greater than the actual actual integral values. Let's talk about the P series. You will love the P series. It's so much fun part and so easy and so simple. And once you learn the P series, you will forget about the other test. Okay, so P series can be applied to only positive terms. P series can be applied to only positive terms. So clearly you can see. Now 1 over n, we just saw on the previous page, is most popular P series. The other name is called harmonic series. We call it a harmonic series. It is the most famous series. Most famous series. Now, why it is called harmonic series? Because it has to do with the string instrument. The length of the string is following this ratio. It is basically a ratio of whole number. Ratio of whole number. So you can make connection with the music and series. That's why this is called most popular P series, always diverge. This is the popular P series, P equal to 1, always diverge. The other name is harmonic series. Okay, so let's talk about the what if P is not 1. So general form, no, this is the general form. I would say again, go back to the unit 6P packet. There we says that if P is greater than 1, series converge. If P is between 0 and 1, series diverge. And if you think about it, it will make sense. If this becomes bottom heavy, again I'm talking about the improper integral. If you have a 1 over n, it's coming slowly, 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 slowly. If you have 1 over n square, it comes down faster and diverge. If you have a 1 over square root n, which means the ratio is between 0 and 1, it is even slower than 1 over n. So that's why P is greater than 1, converge, P is between 0 and 1, diverge. But if we can only say P converge, we cannot find the sum. Remember, there is only one type of series you can find the sum. You can find the sum is only one type of series, which is geometric series. So here, all we have to do is just look at the value and then we can say. So let's practice rewriting. Rewrite 1 and 1/2. So can we say 3/2? And we can say P is 3 over 2 greater than 1, converging P series. That's all. You don't have to do any work. So cool. P series are not bad. The only thing you have to spot them. Why this is a P series? Is that a really P series? So if I rewrite this, then this is n over square root n is square root n. And this is a not P series. This is not P series. This is not a P series. But we can apply nth term test. So limit n goes to infinity. Square root n is infinity and diverges by nth term test. You have to give the name of the test. It's just like you go and to see the doctor and doctor says you are sick, but what kind of sickness? You have to know the name of the disease. So here diverges by nth term test. So this is another look-alike series. If you rewrite, this is 1 over square root n, and you can say P is equal to 1/2, which is less than 1, diverges P series. Diverging P series. If you want a proof, to prove, you can use integral test to prove. To prove this, use integral test to prove, and you will see it diverge. Okay, so how about here? We have such a huge number, 99999 over n to the 1 point something. So remember, this is just the coefficient. You can pull it out. So whatever those 99999, but if I rewrite is actually n to the 1.00001, and the guessing here is whatever that number is, it is still greater than 1. Still greater than 1. So P is, okay, P value is 1.0000000, whatever that number is still greater than 1 and converges by P series test. So P series is one of the easiest tests. You can use them. Tomorrow we will use the P series to compare the other series. So make sure you know this integral test and a P series test. This heading is always generic. All the tests we will have say, if converge, find sum. Remember, sum is possible only geometric series you can find sum. Okay, so let's begin the homework problems, and you are given already the directions on this. The homework is 1, 2, and 3. Make sure you have to use the integral test for problem number 1, 2, and 3. These are some of these P series. P series are here. It's all you have to just recognize. Know that what is the value of P here. If you rewrite this as a 5n square root n, you can identify what's the value of P. Tomorrow we will talk about comparison test. Thank you so much. Good night.